Section 3.5 Dimension. Let W be a subspace of Rn. If this subspace has a basis B given by W1, W2, and so on up to WP, I mean with P vectors, then we say that W is a subspace with dimension P. And we write this means dimension of W. So, if we have a basis, remember that as we covered in previous chapter, in the previous section, a base or a basis for a given subspace is a set that is linearly independent and that spans the subspace W. If that happens, then we have a basis. But if we have a basis, how do we know the dimension for the subspace? Is enough if we count the number of elements. So here, for example, we have P vectors. If we have P vectors, then we say that the dimension for this subspace is P. So it's enough to have if you find a basis, yeah, for a given subspace, you can know the dimension for the subspace. Only count the number of elements in the given basis. Example. Let W be the subspace defined by the vectors such that in the form x2, x3 in R3 such that x1 is negative 2x3 x2 is equal to x3 and x3 any real number. So we have a subspace with all the vectors in R3 in this form. Notice that then for one element in this subspace, it has the form x2, x1, x3, but x1 must be equal to negative 2x3, x2 is the same as x3, and x3 is any number. So notice, if I factor out this with the scalar multiplication, I have x3 times negative 2, 1, and 1. So this means that this is a linear combination of this vector, and this x3 is the coefficient or the scalar. If I choose any number x3, so I can create any vector that is here in this subspace. So this is a base. Because this spans W and is linearly independent. The only way to have 0 when we multiply this vector is if the x3 is equal to 0. So that the vector u equal to negative 2, 1, and 1 is linearly independent and spans W. Then U is a basis for W. And how many elements do we have here? 1. So the dimension for W in this example is equal to 1. Because we have only one element for this subspace. Other example. For any Rn, remember this is all the vectors in the form x1, x2, and so on up to xn with all the x1, x2, and so on real numbers. For this vector spaces Rn, R1, R2, R3, R4, all of them are vector spaces, but we have a standard and canonical basis. The standard and canonical basis is given by E1, E2, and so on, up to En, where E1 is one vector with n elements, but the first entry, and this is indicated by the subscript, is 1, 1, 0, and all the other numbers 0. E2 is 0, the second element 1, and then 0 for the other elements, and so on. An is equal to 0, 0, and the last one is 1. So if we have these vectors, with these vectors, they create a basis for Rn. Then this means that Rn has dimension n. So the dimension for Rn is always n. All right, now some remarks about dimension. The assignment that you are going to see in web work, you will have to respond for the corresponding assignment of this section. Most of the questions or all the questions are basically true or false. So we have to pay attention to mainly to the remarks and of course the definition of dimension that I gave you. But some important remarks. Assume W is a subspace with the dimension of W equal to P. Then, first remark, all the bases for a given subspace not a given subspace, for W have the same amount of elements. The first remark, if W is a subspace, if we know that the dimension for a given subspace P, then necessarily all the bases, they have the same amount of elements. So that is how we can identify or distinguish the dimension, because all the bases, they have the same amount of elements. Other remark, if the basis W1, W2, and so on, WP is a basis for W, then if you add only one more vector, notice I have WP, I added one more, W represented by WP plus 1. If you add only one more vector to the basis, that set is linearly dependent. Other property, any set of fewer vectors than P vectors does not span W. So if we have a set that has less than P vectors, it's impossible that that set can span the subspace W. any set with p vectors that we know is linearly independent is a base for W. So if we already know that the dimension for W is P, if you find a linearly independent set that has P vectors, for sure that is a base for W. And any set with P vectors that we know it spans W is a base for W. All right, let's see one couple of examples with some of these remarks. For example, here, for this example we saw before, for W given by x1 I'm sorry, negative 2x3, x3, and x3. For this subspace, remember one basis was given by the vector negative 2, 1, and 1. Negative 2, 1, and 1. So that if I create another set, the set with the vectors negative 2, 1, and 1, and for example, any other vector, 1, 0, 1, then I know what? This set is not a base, not a basis, and is linearly dependent. So when we have a base and we know the dimension for the subspace W, since the dimension for W is 1, we know that is 1 because we have found a base with one element. Then if you add any other vector to that base, that this is not a base and it's linearly dependent. Yeah. Part B, for R3, we define, remember, the canonical basis, the standard canonical basis, E1, 1, 0, 0, E2 equal to 0, 1, 0, and E3 equal to 0, 0, 1. If we have this, then E1, E2, E3 is a basis. We know that. But if I remove only one, the set, for example, E1 and E2 is not a base. It's not a basis for R3. And it doesn't span R3. So the dimension for this, remember the dimension for R3 is equal to 3. So when you have a base and you remove only one element from the base, we can, for sure, that set is not the basis for the given subspace, or in this case R3, and it doesn't span R3. That doesn't span the subspace. So again, please try to do the exercises in the assignment in WebWork. If you have any question, let me know. See you in the next video.